Hello, I'm Peter Brain. I'm a graduate student at Rensselaer Polytechnic Institute, and I'm here to present on a neutron evaluation for natural lead isotopes in support of next-generation lead-cooled fast systems. This work is sponsored by the Department of Energy Nuclear Energy University program and is in collaboration with researchers at Brookhaven National Laboratory and Naval Nuclear Laboratory. The motivation for this project stems particularly from several commercial and research entities developing fast spectrum systems which will utilize lead or a lead bismuth eutectic as its primary coolant. Using lead as a coolant comes from its significant and unique thermal and neutron properties, which could make it potentially advantageous in fast spectrum systems such as a lead fast reactor. When considering any core material for core use, or in our case lead, it's important to have a high fidelity data set, which you could use along with your transport calculations, such as MCMP, or your lattice codes, such as WIMS, to yield results that are both accurate and have low uncertainty. Looking at the current evaluations and integral measurements done with lead, it's very clear to see that there are some major discrepancies between both the calculated and experimental results. And as such, the goal of the project was formed, and it was to re-examine and re-evaluate natural lead isotopes and to improve the existing NDEF8 evaluation in areas where it needed updating. Finding the areas of the evaluation that needed to be updated and which would have very large impacts towards fast systems was done primarily through fitting previously obtained experimental data and evaluating any new measurements that were made after the release of NDEF8. In all, a international comparative analysis using the different international evaluations was done with both simulated calculations as well as benchmark sensitivities. GEF3.3, GENDL 4.0, and NDEF8 were compared against each other utilizing shielding and criticality benchmarks, lead slowing down spectrometer measurements, which are very sensitive to neutron capture, as well as quasi-differential mid to high energy scattering experiments done here at RPI. This, coupled with the available X4 data sets, led us to find that lead 208 elastic scattering and lead 208 elastic scattering angular distributions were very prominent and major features in both criticality and scattering experiments. Updating the elastic scattering cross-section and the capture cross-sections, as well as recalculating the elastic scattering angular distributions based on updated resonance parameters, yielded a new lead 208 evaluation, which could show improved agreement to the quasi-differential scattering data seen here in red. Below 1 MeV, we have very much improved agreement with the scattering data. And in terms of criticality, we see that this RPI evaluation for lead 208 improves criticality over NDEF8 and GEF3.3 for fast systems. Future work will revolve around this 1 to 2 MeV region, where we see a major breakdown in the ability of the simulation to predict the scattering data, and this will be a combination of exploring the optical modeling of the inelastic states for 206 and 207, as well as extending the resolved resonance region for lead 208 to gain similar angular distributions that we used below 1 MeV. And these are all in the hope to obtain better physics and better agreement with the physics that will then in turn yield better K-effective calculations for both thermal and fast criticality systems. Thank you.